Jai Hind everyone. Myself Dr. Suvarna Mujumdar welcomes to a lecture on Synchronous Counter. So we are going to discuss here about the design of a synchronous counter, and here I have taken the example of mod 10 counter. And here I can say that the mod 10 counter is nothing but it is a decade counter or a BCD counter, or we can say as binary coded decimal counter. Mod 10 specify that this counter will have an 10 state. So the 10 state means it will count from 0. So it will count from 0, 0, 0 and the maximum state will be 9, that is 1, 0, 0, 1. So we can say there are 10 states from 0 to 9, and that's why we call this counter as a mod 10 counter. And as it is a decade 10 states, so we can call it as a decade counter also, and BCD, that is binary coded decimal. So counter is basically a sequential circuit which will use to count a sequence, or we can say the pulse. And any generalized case, mod n counter, here we can say it will count from 0 to n minus 1, because 0 is one state, initial state. So the total states are n, but the maximum value, maximum count will be n minus 1. So this we can find how we can design this synchronous counter. And before going to design part, we have to discuss about the counters. There are two types of counters generally, that is, one is known as asynchronous counter, or we can call it as a ripple counter, where flip-flops triggered sequentially, means one flip-flop will initialize the triggering of another flip-flop, and that we don't have any synchronized clock between them. They all are working with the sequential manner. But in case of synchronous counter, which we are going to discuss in this lecture, it is in this counter, all the flip-flops are triggered simultaneously, or we can say there is the same clock applied to all the counters. And this is faster as compared to asynchronous counter, and more reliable also. So in many circuits where we need a timer or where we need a clock, in that case we use synchronous counter, and mostly mod 10 or decade counter, or I can say BCD counter is used, because it will count from 0 to 9, and it will be easy to recognize it as a counter. So design steps for design any synchronous counter, whether it is mod n or 3-bit counter or 8-bit synchronous counter, the steps are as follow. First, we have to find the number of states, and we have to draw the state diagram. This is the first and foremost step. Then we have to calculate the number of flip-flops required. By using the maximum count, we will find the number of flip-flops required. Then we have to select the flip-flop. We have studied 4 flip-flops: SR, JK, D and T. T is a toggle flip-flop, D is a delay flip-flop, JK flip-flop and SR flip-flop. Out of these 4 flip-flops, generally we use 3 flip-flops, JK, D and T, to design a counter. Specifically, I can say if we are designing an asynchronous counter, then it is mentioned that use T, that is toggle flip-flop, because in that case all the flip-flops are sequentially programmed. So we use T flip-flop, which is generally an easy flip-flop, and toggle for each values of the input. If T is changing to 1, it will toggle. In case of synchronous counter, it is not specified that we have to use T or D. So there are 3 flip-flops. We have to select JK, D or T. In this particular lecture, I am going to design mod 10 counter using JK flip-flop, but you can design using D also or T also. I will say if it is not mentioned that which flip-flop is used, generally refer D flip-flop, because delay flip-flop follows, or we can say it is a easiest flip-flop to remember, and its output depends easily on input. Whatever the D value, output will be that value. Then after selection of the flip-flop, we have to draw a state transition table. From this state transition table and using excitation table, we will find the input for the flip-flop. Whichever flip-flop we choose for that particular flip-flop, we have to use the excitation table of that flip-flop, and then in that case, we will find the input flip-flop. After finding the input of the flip-flop, we will solve the input equation using K-map, and we will obtain the equation using K-map. When we got the input equation, we draw the logic diagram, and for for the explanation or for the understanding the working of this counter, we will draw the timing diagram. So, we will start with the first step, that is the number of state. So, in case of mod 10, we will find that it is a 10 state and it's 10, and the states are start from 0, 000, or I can say for representation it is 000 to 1001, or in the state diagram it is starting from 0 to 9. So, there are 10 states which we are going to use. So, this is a state diagram. You can represent it with the states or you can represent it with the binary value also, like this. It all depends on you how you can represent state diagram representation, whether you are using binary value or whether you are using the decimal value to represent the state. Even you can use a variables ABCD to represent the 10 state. But generalized way, we can use number or we can use binary way for this counting. So, here I have represented it as a decade counter, but this will be applicable for BCD or mod 10 for all the three, or we can say this is the one. After doing state diagram, we obtained that the number of states are 10. So, number of flip-flop, to find the number of flip-flop, we have to use the representation like this, where n represent the number of flip-flops. So, here n, capital N is 10. So, if we substitute here n equals to 4, it is 16. Sorry, this will be, I have written this wrong way. So, it will be like this. Okay, so 16, so 4 we will use like other. If I use 3, then this condition will not be satisfied. So 3 flip-flop will not represent the 10. So here we need 4 flip-flops. Now we have to select which flip-flop selection. So depending on your requirement, you can choose D flip-flop if it is not mentioned, or you can use T flip-flop or JK flip-flop. In this particular lecture, I am going to cover JK flip-flop, but generally you avoid using JK flip-flop because it means for each flip-flop you have to solve 2 K-maps. But it means in particular this case, as we required 4 flip-flops, so I have to solve for JK, JB, KB, 4 input JC, KC and JD, KD. I need to solve, I have to find 8 equations, input equation. But if you use D or T, in that case you have to solve 4 input equations only for each case. Okay, so it will be easy. Circuit diagram will be easy, but just to go with the toughest one, I have chosen JK flip-flop for this case. So now the next step is we have to draw the state transition diagram or state transition table. State transition table consists of first 2 columns, which is known as, first is known as present state, next state. Present state, as I told, we use 10 states. To represent 10 states, we need 4 flip-flops. So, I named it as A, B, C, D. And corresponding next state, I represented it with A plus. You can represent it with A T plus 1. Here you can represent it T. Then the next state will be A T plus 1, something like that. Present states, we represent 10 states starting with 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, in this way, we have written 10 state. From 0, the next state will be 1. For 1, the next state will be 2. For 2, the next state will be 3. For 3, next state will be 4. For 4, 5, 5, 6, 6, 7. So, 7 will be next state for 6. For 7, it is 8, 9 and for 9, it will be the 0 because we have to complete the circle. From 9, it has not to go to 10 state, it has to go to 0 state, and again the counter will start. So, this is the state transition table. From this state transition table, now we will choose excitation table and we will obtain the flip-flop inputs. In case of excitation table, we have to refer the excitation table of JK flip-flop. So, excitation table is present state to next state, excitation table. To travel from present state to next state, what will be the input combination? This is representation in the excitation table. So, if you are at 0 state and you have to remain at 0 state, your input should be 0 cross x. If you are at 0 state and you have to move to 1 state, like in this case, this is the case, third one, okay. So, in this case, your input should be 1 cross x. You are at 1 state and you have to go to 0 state, then this will be the case. It will be cross 1. And if you are at 1 state and you have to remain at 1 state, this is the case, it will be cross 0. So, we use this excitation table and we find these values. So, for all zeros and we have to remain in 3 are the zeros. So, it is 0 cross 0 cross 0. And here in case of D, it is toggling from 0 to 1. So, we have to give input as 1 cross. This cross is nothing but a don't care condition, which will be either 0, considering it 0 or 1. As we are mapping it for SOP combination, we always considered it don't care as a 1 value. Here, this excitation table represents that if k is 0, then also you remain, that is no change. And if k is 1, then also you reset the output. So, in both the cases, your output will be 0. That is the next state. So, that is why we represent it as 0 cross. Okay. So, from this table, we have find the flip-flop input, and for each flip-flop input, we will solve the K-map. So, for JA, you will see that for this case, JA, for 7, the output is 1. Sorry, the flip-flop input is 1. For 8, it is don't care, and for 9, it is don't care. So, in this table, you can find that for 7, it is 1. And for rest of the input also, after 9, that is 10, 11, 12, 13, 14. For these cases, up to 9, we have the output, the value of JK or K, that is the input, flip-flop input. But after 9, the condition for 10, 11, 12, 13, 14 and 15, for these combination of the inputs, or we can say for these combination of A, B, C, D, we consider all the output should be don't care. So, for each K-map, for all the 8 K-map, for these values 10 to 15, we represent don't care. 8, 9, 10, 11, 12, 13, 14, 15. Okay. And we have to pair for 1 only. So, in case of JA, only 1, 1. So, we pair it and we will find the equation as BCD. In case of K, the 1 is only at 9th position. So, we substitute here the 1 in 9th position and we substitute K also. The K, don't care, these don't care, whatever the value is. So, find this, we find that this will be an octet and this octet will give us the value D. Similarly, we solve for JB, KB, JC, KC, JD and KD. For JD and KD, as these are the lowest flip-flop, or I can say LSB position flip-flop. So, in case of counter, we always found that the LSB position flip-flop toggle for each clock. So, that's why every time we find that JD and KD is equals to 1, that for each clock their value should be 1, so that they can toggle for each clock. First it is 0, then 1, again 0, then 1, because we get in timing diagram we will find that for this flip-flop will change for each clock. Other flip-flops depend on the counting value, whether we need 1, 2, 3, but you can find here this case D is changing for every position. So this flip-flop, the inputs will be changing, that will be, must be 1. So from this equation, we will draw this logic diagram. So here if we will find that JA is BCD. So we need one AND gate which will ANDing this BCD. Here BCD, these are the output from B flip-flop, C flip-flop and D flip-flop, or you can say it as a QB, QC and QD. So the output of this B, C and D, these are connected here. You can write it, if you write here QB, then in that case you have to write here QB, QC, QC, QD. If you are writing here. So what will be the output from each flip-flop? We are considering here. In case of KA, it is D. So you can directly connect this D here, or you can write this D. If you are using QD, then you can write it as QD. JB is CD, KB is again CD. So both are having, and you can use one AND gate and the output is given to both of this. So like this, we are using only one AND gate and the output of this AND gate is given to JB, KB. In case of, this JB and KB, JC and KC, your JC is A bar D, so we need one more AND gate, and in KC again we can connect directly the D. And for D flip-flop, JD and KD both are connected to 1. So logic 1 means VCC or high, you can say. So this is the logic diagram, and as I told, this is a synchronous BCD counter. So the clock of each flip-flop are common. And here we are using negative edge or edge triggered flip-flop, which will give us good results, because in case of level triggered flip-flop, the output toggles and we are getting a race around condition. So we mostly prefer in the counter edge triggered flip-flop, and in edge trigger again we use negative edge trigger when we are going from up counting. If we are going for down counter, we will use positive edge trigger. So negative edge trigger flip-flops are used J and K. You can use T flip-flop, you can use D flip-flop, and you can draw this logic diagram. Now the next we have to discuss about its working. So as I told, all these flip-flop are synchronized in nature. So the same clock is applied. So this will be the clock applied to all the flip-flop. Okay. This will be the initial condition. A, this will be A flip-flop, B flip-flop, C or D. It will be in decrement order. It will be something I have written. This will be A, maximum. Q3 will represent MSB and Q0 represent the LSB. Okay. So as I told, that D flip-flop will toggle for each clock. So this will be the first clock, negative edge. For this, it will toggle from 0 to 1. For second clock, it will travel from 1 to 0. Third, 0 to 1, 1, 0. Okay. So it will toggle for each clock pulse. In case of C flip-flop, you can see here, C flip-flop will depend on the value of A bar and D. As D is changing for each one, A bar means A bar will be 1 because A is 0. So D will changing. So depending on D, JC will toggle. So for here you can see that as it is traveling to 1, its value is 0. But for this clock pulse, it is 1 and it is 0. 0 is complemented to 1. So both are 1 and we get the result 1. And this 1 will remain 1 for second clock also. This transition. So here 0 to 1. For this case also you are getting 1. But for this case, for this value, it is 0. So the C will converted to 0. And here we again get 0. For this clock, we get value 1. Okay. B will toggle after 4 clock pulse and it will remain for 4. It will remain high. and A will toggle after 8 clock pulse, and this will be, so you can find here 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, and after 9 it again goes to 0. So this way your synchronized mod 10 counter, or you can say decade counter, or you can say BCD counter works. This is all about the design of a synchronous counter. Thank you.